Big Boy 4014 draws tens of thousands to the trackside every time it moves. The most famous locomotive on Earth. But there was a Union Pacific locomotive even more powerful, and almost nobody remembers it. It was longer, louder, and at 8,500 horsepower, it dwarfed anything the Big Boy could produce. Union Pacific called them gas turbine electric locomotives. Crews called them the Big Blow. They were built to be the Big Boy's successor, the next generation of giant railroading. And then they vanished. Every last one scrapped, erased from the story. So what made Union Pacific gamble everything on a machine like this in the first place? The answer begins with a machine unlike any other to ever run on rails, the gas turbine electric locomotive, or GTEL. Introduced in its most powerful form in 1958, this three-unit Leviathan stretched exactly 165 feet and 11 inches. It operated as a three-unit set, combining a cab unit, a turbine power unit, and a massive fuel oil tender. This massive assembly generated 8,500 continuous horsepower, a figure that remains the highest output of any single locomotive in American history. That is 4 times the power of the standard diesel engines of that era. Yet, while the steam-powered Big Boy is celebrated worldwide, the GTEL has largely vanished from public awareness. To understand this machine is to examine a specific moment when railroads turned away from coal and water, but had not yet committed to standard diesel designs. General Electric built these units to haul massive freight tonnage across the open spaces of the West. At their peak, 30 of these third-generation locomotives roamed the Union Pacific system, easily identified by their deafening roar and the heavy fuel tenders they dragged behind them. Crews quickly named them the Big Blow because of the jet engine howl that announced their arrival miles before they could be seen. They represented the peak of raw industrial traction, moving 5,000-ton freight trains without assistance. But within a decade, this entire fleet went from the pride of the Union Pacific to scrap metal. Only 2 survived, kept as silent, static displays. The rest were systematically cut apart and sold for parts. How a record-setting giant became a footnote in transportation history is a story of extreme engineering meeting a changing economic reality. The justification for this colossal experiment lay in the rugged topography of the American West. Union Pacific's primary transcontinental artery, stretching from Council Bluffs to Ogden, faced a daunting geographic bottleneck, the Wasatch Grade. This route required trains to climb a sustained 1.14% incline for 65 continuous miles, rising over 2,500 feet into the Utah mountains. For a railroad tasked with moving the nation's heaviest industrial freight, this single stretch of track was a constant, punishing battle against gravity. In the mid-20th century, as the age of steam drew to a close, the emerging alternative was the diesel-electric locomotive. However, early diesels of the 1950s were relatively weak, producing only 1,500 to 2,000 horsepower each. To move a massive, multi-thousand-ton freight train up the Wasatch Grade, Union Pacific had to couple 5 or more of these diesel units together. This setup, known as a lash-up, created a logistical nightmare. Multiple engines meant multiple mechanical systems to maintain, more points of potential failure, increased fuel complexity, and higher overall operating costs. Union Pacific's corporate philosophy had long favored concentrated power. Instead of managing a complex team of smaller engines, the railroad's planners wanted a single, massive locomotive that could do the work of an entire fleet. They measured efficiency in gross ton miles per train hour, a metric that demanded high power density. The goal was to hook one ultimate machine to the front of a heavy freight train and run it straight over the mountains with minimal fuss. In this environment of steep grades and endless horizons, the search for a single unit powerhouse made perfect, cold calculating economic sense. The gas turbine represented the railroad's best bid to conquer the West on its own terms. In the late 1940s and early 1950s, Union Pacific faced a quiet crisis at the core of its operations. The massive steam locomotives that had won the war and built the railroad's reputation were rapidly wearing out. The workhorse Challenger fleet, which had dominated fast freight service since 1936, was nearing the end of its economic life under punishing tonnage. At the same time, the celebrated Northern-class locomotives, which had handled high-speed passenger and fast freight runs, were losing their place on the roster as passenger service declined and early diesels began claiming the flatland routes. Steam was retreating across the entire system, leaving a massive power vacuum on the steep mountain divisions. This transition left no room for compromise. Union Pacific required a successor equal to the legacy of the giants it was retiring. The railroad had built its modern identity on unmatched single-unit power, culminating in the articulated big boy. To replace these giant machines with long lines of small, identical diesel units felt like a step backward to the railroad's planners. They needed a new titan, a single locomotive that could inherit the mantle of the steam era and carry it into the future. The gas turbine program was designed not as an experimental side project, but as the official heir to this giant steam tradition. When Union Pacific retired its last steam locomotives in July 1959, including Challenger units and Big Boy number 4015, the railroad positioned the turbine as the logical next step. It was built to run on the exact same mountain routes, haul the same crushing tonnage, and command the same awe as its steam-powered ancestors. This program represented a deliberate attempt to preserve the railroad's grand tradition of concentrated strength, swapping the firebox for a turbine. To understand the physical operation of the Big Blow, we must look beneath its yellow steel casing at an engineering layout that owed more to aviation than traditional railroading. At its core, the locomotive was a massive, modified jet engine mounted inside a boxcar frame. But while an airplane engine uses expanding exhaust gases to create forward thrust, the turbine inside this locomotive converted that high-temperature thermal energy into raw, rotational force. The heart of this system was a General Electric frame, 5-axial flow gas turbine. The mechanical cycle began at the front of the turbine unit, where a multi-stage compressor pulled in enormous volumes of outside air, squeezing it to a fraction of its original volume. This highly pressurized air was forced directly into a series of combustion chambers, where it mixed with fuel and ignited. The resulting high-energy gas expansion rushed backward, spinning the blades of the turbine wheel at thousands of revolutions per minute. Instead of escaping through an exhaust nozzle to push the locomotive forward, this rotational force was captured by a central drive shaft. This shaft was coupled to a set of heavy-duty, high-speed electrical generators. The generators acted as a massive energy converter, transforming the physical spinning of the turbine shaft into a torrent of electricity. This electric transmission system made the gas turbine a highly efficient power plant on wheels, generating massive electrical current on the move. From the generators, this electrical current traveled through heavy copper cables down to the locomotive's steel wheel trucks. Mounted directly on the axles were 12 traction motors, specifically the rugged General Electric 752 E3 model. These electric motors received the high-voltage current and turned the wheels, delivering a continuous tractive effort of 145,000 pounds to the rails. By spreading this power across 12 driven axles in a CC plus CC arrangement, the locomotive could deliver its massive torque to the rails without losing traction on steep mountain grades. Operating this complex machine, however, required a carefully coordinated routine. A gas turbine cannot start from a dead stop on its own. It requires a massive amount of external force just to begin spinning the compressor fast enough to compress air and sustain combustion. To solve this, General Electric installed an auxiliary diesel engine, commonly known to crews as a donkey engine. On these third-generation units, this was an 850 horsepower Cooper-Bessemer engine. During the startup sequence, the Donkey engine was fired up first. It cranked the main turbine shaft, slowly building up rotational speed until the turbine could draw in enough air to support fuel ignition. Once the turbine fired and took over, the Donkey engine could be dialed back. But its job was not finished. It continued to run, powering the onboard support systems including air compressors, battery chargers, and radiator cooling fans. More importantly, the Donkey engine provided just enough electrical power to move the locomotive at low speeds around service tracks and rail yards. This allowed crews to reposition the massive machine without having to fire up the main, fuel-thirsty turbine, saving fuel during routine yard movements and keeping the giant turbine quiet until it was time to head out onto the main line. This elegant but complex combination of diesel, turbine, and electric technology created a mechanical giant capable of unprecedented performance. To look at one of these third-generation machines was to confront a physical impossibility on rails. While a standard diesel-electric locomotive of the late 1950s was a self-contained box, this ultimate gas turbine electric locomotive required three distinct, massive segments coupled together. Up front rode the control unit, housing the operating cab and the auxiliary diesel engine. Behind it coupled the heart of the beast, the turbine unit itself, a windowless steel vault enclosing the massive General Electric Frame 5 turbine and its dual generators. Snapping at its heels came the insulated fuel tender, a recycled, steam-era giant carrying 26,500 gallons of thick fuel oil. This configuration rejected the streamlined aesthetics of the passenger era, presenting instead a rugged, utilitarian silhouette that prioritized brute force over beauty. The total assembly stretched exactly 165 feet and 11 inches. This massive footprint made the locomotive longer than a standard passenger train car, and nearly the length of a Boeing 747. It was an iron wall on wheels, weighing an astonishing 849,212 pounds. When fully loaded with fuel, water, and lubricants, this three-unit set pressed down on the steel rails with more than 420 tons of dead weight. Yet this immense physical mass was entirely justified by the numbers generated inside the turbine chamber. The third-generation units possessed a continuous rating of 8,500 horsepower. In short bursts, during the most punishing climbs up the mountain, engineers could coax the system to deliver an astonishing 10,000 peak horsepower. To put this into perspective, the dominant diesel road switchers of the late 1950s, such as the Electromotive Division GP9, produced only 1,750 horsepower. A single gas turbine locomotive exerted the raw pulling force of more than 4 of these standard diesels combined. Union Pacific's planners had wanted a single-unit powerhouse to replace complex multi-locomotive lash-ups, and General Electric delivered exactly that. 12 traction motors down below, geared directly to the heavy axles, translated this immense electrical output into raw movement. Spreading this extreme energy across 12 driven axles, the locomotive delivered a continuous tractive effort of 145,000 pounds. It was a level of concentrated power that had never been seen before on an American railroad and has never been equaled since. The machine was designed to do the work of an entire fleet, acting as a single, unstoppable force at the head of a mile-long freight train. But physical scale and paper specifications only tell part of the story. The true impact of this machine lay in its sensory assault, a combination of heat and sound that made the turbine an unforgettable and increasingly problematic presence across the towns and canyons of the American West. To stand near this machine was to experience an acoustic assault that redefined what a railroad could sound like. Traditional steam engines chugged and hissed. Early diesel units hummed with a rhythmic, low-frequency throb. This locomotive did neither. It screamed. The exhaust note was not a mechanical pulse, but a continuous, high-velocity jet engine shriek, because the core of the locomotive was built around an axial flow gas turbine. The escaping gases exited the roof-mounted exhaust stack at blistering temperatures, rushing skyward with the fury of an aviation power plant. At idle, the sound level measured a staggering 120 decibels. This was not merely loud, it was the threshold of physical pain. Crews and trackside observers did not just hear the turbine, they felt it. The sheer volume created a low-frequency vibration that rattled windows, shook ground, and resonated deep inside a person's chest. Long before the yellow nose of the locomotive appeared around a mountain curve, its presence was announced by a physical pressure wave traveling through the air. The roar could be detected from miles away, echoing off canyon walls and rolling across the open prairies of Wyoming and Utah. It was this inescapable howling gale of exhaust that earned the locomotive its enduring nickname, the Big Blow. The moniker was not coined by corporate public relations, but by the railroaders who worked alongside it and the communities that lived near the tracks. It was a title earned through raw, deafening volume, a sensory identity that distinguished this mechanical giant from ordinary railroad power. In 1962, the Los Angeles City Council enacted an ordinance that banned these gas turbine locomotives from operating within city limits. The jet-like howl was no longer celebrated. It was treated as a civic threat. In residential areas along the tracks, the constant vibrations rattled windows and disrupted sleep, provoking a public backlash that local officials could not ignore. This municipal ban forced Union Pacific to banish the fleet from its southern corridor. The railroad rerouted the locomotives, confining them to the line between Council Bluffs, Iowa, and Ogden, Utah. While standard diesel engines could idle quietly in metropolitan rail yards, the turbines screamed at 120 decibels even when standing still. Operating them near populated communities became impossible to justify. The signature feature that defined the machine's unmatched power had transformed into a liability, turning a symbol of industrial strength into an excluded public nuisance. To feed the massive turbine, Union Pacific bypassed standard diesel in favor of a cheap, heavy residue from the petroleum refining process. This was Bunker C, a thick, dark substance that resembled cold tar more than a usable liquid fuel. Though the railroad sometimes utilized a slightly cleaner No. 5 heavy fuel oil to protect the turbine blades from corrosive wear, the fuel retained its stubborn, tar-like character. At room temperature, it was so highly viscous that a person could walk across a pool of it without sinking. It was the heavy waste left at the bottom of the refining barrel, cheap to purchase, but incredibly difficult to handle. To make this substance flow through the fuel lines and atomize inside the combustion chambers, the locomotive had to keep it constantly hot. The massive tenders, recycled from steam locomotives, were fitted with internal steam-heated coils. Steam from the onboard auxiliary boiler ran through these coils, heating the heavy oil to nearly 200 degrees Fahrenheit before it could even move. This requirement introduced a permanent operational hazard to everyday railroading. If the fuel temperature dropped too low, the oil would solidify inside the tender, clogging the intake pumps and choking the turbine. Crews had to constantly monitor the tender's heating systems. If a turbine sat idle for too long in the freezing winter of Wyoming, the fuel would freeze into a solid block of asphalt, requiring hours of manual heating to liquefy it again. What began as an effort to use cheap industrial waste became a built-in operational complication that defined the daily life of every turbine crew. To carry this massive volume of heavy, preheated oil, Union Pacific bypassed the expensive option of building entirely new equipment. Instead, the railroad looked to the very machines the gas turbines were designed to replace. In the Salt Lake City shops, beginning in late 1955, Boilermakers and machinists began converting the giant steel tenders from retired steam locomotives into specialized fuel carriers. Workmen stripped the water compartments from the 18C and 20C class tenders of retired Challenger and Northern locomotives. They added thick layers of insulation, installed internal steam heating coils to keep the heavy oil fluid, and modified the coupler arrangements. These rebuilt cars, now designated as Class 24C GTE fuel tenders, had their capacities expanded to hold 26,500 gallons of heated fuel. This conversion bound the two eras together, as these roaring, futuristic turbines screamed across the western plains. They did so while physically coupled to the heavy steel underframes of the steam giants they had just driven into retirement. The physical remnants of the steam age were kept alive, rolling directly behind the jet age technology that replaced them. For a brief window in the late 1950s and early 1960s, this unprecedented engineering gamble paid off exactly as Union Pacific's planners had calculated. The economics of the era heavily favored the turbine. While refined diesel fuel prices fluctuated, the heavy residual oil that powered these machines remained incredibly cheap. Because it was essentially an industrial byproduct, this heavy fuel oil allowed the railroad to move massive tonnage at a fraction of the fuel cost of equivalent diesel operations. Beyond the cheap fuel, the turbine delivered an unmatched concentration of power. A single 8,500 horsepower turbine electric set replaced 5 conventional diesel locomotives. By consolidating all that tractive effort into one machine, Union Pacific dramatically simplified its operations over the Wasatch Grade. Fewer locomotives meant fewer mechanical components to maintain, reduced total locomotive mileage, and simplified train handling for the crews. Instead of managing 5 separate engines, a single crew controlled one massive, continuous power plant. This early success created immense confidence within Union Pacific's motive power department. The turbines were not treated as experimental novelties. They became the hard-working backbone of the Mountain Division, routinely racking up millions of cumulative miles. For a railroad defined by long-haul bulk freight, the giant turbine was not a mistake. It was a highly logical, highly effective solution to a specific geographic and economic challenge, proving itself as a viable master of the mountain routes before the underlying equations began to shift. The mathematical equation that made the gas turbine look so attractive on paper began to fall apart the moment the locomotive stopped moving. Unlike a diesel engine, which can drop to a low, quiet idle to conserve fuel, a gas turbine must maintain a high rotational speed to keep its compressor functioning and its combustion cycle self-sustaining. This meant the giant Frame 5 turbine devoured fuel at an alarming rate, even when sitting completely still on a passing siding or waiting in a yard. At full load, the turbine gulped 15 gallons of fuel every minute, but its idle consumption was the real economic leak. The machine burned nearly half of its maximum fuel rate just to keep itself spinning at a standstill. While a 5-unit diesel lash-up could idle efficiently for hours, a single turbine waiting for a clear signal was actively draining its 26,500-gallon tender. This constant, insatiable fuel burn floor steadily eroded the cost savings achieved while pulling heavy tonnage up the mountain grades. An even more destructive problem was occurring hidden inside the turbine chamber itself. The cheap, heavy, residual fuel oil that gave the locomotive its low operating cost carried a hidden chemical tax. This heavy oil contained high levels of sulfur, sodium, and vanadium, impurities left behind at the bottom of the petroleum refining barrel. When burned at temperatures exceeding 1,000 degrees Fahrenheit, these elements transformed into highly corrosive chemical compounds. As these hot, pressurized gases rushed through the turbine, the vanadium and sodium compounds liquefied, forming microscopic slag that deposited directly onto the spinning turbine blades. This process, known as hot corrosion, chemically attacked the specialized metal alloys of the blades, eating away their protective surfaces. Combined with the abrasive physical wear of unburned carbon particles, the turbine blades suffered rapid erosion. The precise aerodynamic profiles of the blades warped and degraded, reducing the power plant's overall efficiency. Compounding this physical erosion was the mechanical stress of thermal cycling. As engineers opened and closed the throttle to manage train speeds over rolling terrain, the temperature inside the turbine chamber swung rapidly by hundreds of degrees. These extreme thermal shifts caused the metal blades to expand and contract, initiating microscopic stress cracks at the blade roots through thermomechanical fatigue. To prevent catastrophic blade failures, Union Pacific had to implement an aggressive and expensive maintenance regimen. The locomotives required frequent, highly specialized overhauls in dedicated shops equipped with precision diagnostic tooling. Mechanics had to tear down the massive turbines, inspect every individual blade stage with non-destructive testing, and replace compromised components long before their projected service lives were reached. The complexity of these high-temperature alloy systems meant that maintenance was no longer a routine matter of replacing filters and gaskets. It was a constant struggle to keep the locomotive's core from self-destructing. The financial advantage of burning cheap fuel was being systematically eaten away by the mounting cost of keeping these high-strung, aircraft-derived power plants in working order. The decisive blow to the gas turbine program came from the global oil market. Throughout the 1960s, the price of heavy residual fuel oil began to climb, systematically erasing the cost advantage that had once justified the turbine's voracious appetite. What was once a cheap refinery waste product became a valuable commodity for industrial heating and marine shipping, driving the price upward and exposing the turbine's massive fuel consumption. At the same time, the rapid development of second-generation diesel locomotives fundamentally changed Union Pacific's options. Diesel technology had matured. New, highly reliable units like the Electromotive Division SD40 and General Electric's own U-Series produced high horsepower with exceptional fuel economy. By coupling 3 or 4 of these modern diesels together, the railroad could easily match the 8,500 horsepower of a turbine. These diesel sets could idle efficiently, required no complex preheating equipment, and could be serviced in any standard railroad shop across the country. By 1968, the economic math no longer worked. Union Pacific began withdrawing the turbines from service. In August of that year, the first 4 units were retired. Others followed in rapid succession. The last revenue run of a Union Pacific gas turbine occurred on December 26, 1969. When turbine number 7 hauled a freight train from Cheyenne, Wyoming to North Platte, Nebraska. By February 1970, the entire fleet was retired. The railroad sold 10 units to a leasing company for scrap and traded the rest back to General Electric for parts. The roaring era of the big blow was over. The silence of the turbines proves that history isn't won by raw power, but by what stirs our imagination. We still worship the romantic hiss of steam, while the chest-rattling roar of this jet-age giant is lost to time. In the end, the big blow didn't just burn fuel, it consumed its own legacy. Was it a magnificent failure, or the true king of the rails? Let us know in the comments.